Welcome back, builders. You are tuned in to another explainer produced by Forge College. Today, we're continuing our journey from the EVM to the SVM, specifically transitioning your skills from Ethereum over to Solana. We're right in the thick of our module, Capstone, developing a Solidity-to-Rust and Anchor code pattern catalog, and today's focus is defining translation rules and priorities. Honestly, think of today's explainer as a mad scientist's blueprint. If you're going to take EVM code and mutate it into SVM code without having the whole thing explode in the lab, you absolutely need a strict, repeatable schematic, and we are going to ink that blueprint today.
Okay, so here is how we're going to lay this out. First, we'll set up the translation blueprint. Then, we'll measure things up using the 5 translation axes. Third, we'll walk through our exact 4-step workflow. From there, we'll head to the test bench to see the blueprint in action, and finally, we'll lock it all in with the golden rules.
All right, let's dive right into part 1, the translation blueprint.
In our previous lesson, we framed up the basic structure of our catalog. But here's the thing, attempting ad hoc code translation without strict rules is literally like trying to build a spaceship without a schematic. Sure, you might get off the launch pad, but you definitely won't survive the vacuum of space. So that brings us to the fundamental question we have to ask for every single piece of code. Do we preserve the original shape, which we call fidelity, or do we completely remodel it into an idiomatic rewrite optimized specifically for Solana?
To answer that, we really need to nail down exactly what fidelity means in our rulebook. When we say high fidelity, we mean strictly preserving the original observable behavior, maintaining off-chain compatibility for external tooling, and keeping the API shape of the Solidity construct as intact as possible. And here's the kicker. Sometimes you have to do this even if it means sacrificing those clean, beautiful Rust ergonomics. It's a trade-off. We have to know exactly when to perfectly copy the old shape versus when it's safe to totally optimize and rewrite.
Which perfectly sets up our next step. Let's move to section 2, the 5 translation axes.
To actually make that tough decision between fidelity and an idiomatic rewrite, we need a measurement system. Think of these as the baseline laws of physics for moving from Solidity to Rust and Anchor. We measure across 5 axes: ownership, storage, error handling, events, and API shape. Now, for each of these axes, we have a target mapping. For instance, ownership maps directly over to explicit accounts in Anchor. But most importantly, we have a priority guideline. Are we preserving semantics, emulating behavior, or going for a full idiomatic refactor? This right here is your master decision matrix.
Now, what's really interesting here is the stark contrast between these two paradigms, especially when you look at ownership and storage. Solidity relies incredibly heavily on implicit control. Think about msg.sender and shared storage states. Anchor, on the other hand, demands explicit control through account constraints, typed accounts, and PDAs. It's actually kind of funny when you compare them. Solidity is like a nightclub bouncer just glancing at people and guessing the guest list based on who walked through the door. But Anchor is like a high-security vault that demands a cryptographic VIP pass before you even step foot on the property.
Running through the rest of the axes on our blueprint, we look at error handling, events, and API shape. For errors, we're completely moving away from raw string reverts. Instead, we use typed anchor errors, mapping Solidity's require statements straight to Anchor macros. When it comes to events, this is where fidelity almost always wins. If your off-chain tooling relies on specific event names and index topics, you've got to preserve them. And finally, API shape. This one's a balancing act. You're constantly weighing the need to preserve the legacy application binary interface for migration tools against the desire to refactor everything into clean, modular, idiomatic Rust instructions.
So we have our theory down. Let's operationalize this in section 3, the 4-step workflow. This is the exact chronological assembly line process we use for every single contract to prevent our translated code from failing on the launchpad. Step 1, annotate the snippet. Go in and identify persistent storage, view-only functions, and msg.sender calls. Step 2, apply access rules. Use the matrix we just talked about to decide your target mapping and priority. Step 3, produce code and rationale. This is where you actually write the Anchor code and jot down a short paragraph explaining the trade-offs you made. Finally, step 4, review checklist. Double-check your signer constraints and migration notes. It's systematic and it works.
Enough theory, right? Let's take this to the test bench. In section 4, blueprint in action.
We are going to apply our blueprint to translate the absolute classic Solidity ownership pattern. In Solidity, you'd usually have an entire block of imperative access control code manually checking require msg.sender equals owner right inside the function body.
But in Solana, that whole chunk condenses down into a single, beautiful, declarative anchor macro, an account macro specifying mute and has1 equals owner. This tells the program to validate that the provided owner matches the stored owner before the instruction even thinks about executing. It is incredibly elegant, totally declarative, and highly secure.
Let's break down the exact translation choices we made for this ownership widget. First off, we prioritized high fidelity for security by completely replacing those implicit msg.sender checks with explicit signer constraints. Second, we mapped the contract state directly to a single typed anchor account, perfectly applying our storage access rule. Third, we preserved the ownership transferred event verbatim because we know external ecosystem tools are definitely going to rely on it. And fourth, because we embraced Anchor's native declarative macros, our actual function body is super minimal. All the heavy lifting is handled by that pre-instruction validation. We successfully balanced security fidelity with idiomatic anchor mechanics.
Let's synthesize all of this in our final section, the golden rules.
The crucial takeaway today is that these 3 rules form the baseline mental model that will guide literally all your translations in the catalog. Rule 1. Always prioritize declarative constraints for ownership and security. Make it explicit, no guessing. Rule 2. Default to single-typed anchor accounts for your storage unless size limits or dynamic mappings force you to split them up. And Rule 3. Be a good citizen to your off-chain tooling. Preserve those revert messages and event topics when external systems depend on them.
To really cement this idea, I want you to remember this quote. When a catalog entry requires high fidelity for auditing, preserve semantics. For greenfield use, allow API shape and internal layout refactors. In the end, context is king. Your translation priority has to match the ultimate end goal of the project you're working on.
As we wrap up, I want to leave you with this provocative thought to chew on. Are you merely translating syntax, or are you faithfully translating intent? Because a truly great developer does the latter. Keep that question in the back of your mind as we move into our next lesson, Guided Translations of Core Patterns, where we are going to apply this rulebook live. Thank you so much for joining this explainer, produced by Forge College. If you want to master these concepts and explore even more deep dive Web3 topics, I highly encourage you to visit forge.college. See you in the next one, and happy building.